So good morning, everyone. I think we can start, so please be seated comfortably. I'm glad to have the opportunity to welcome you at Pedestrian Evacuation Dynamics 2025. And before we start with the first keynote talk, I would like to give you some short information where you are. So, welcome to Czech Technical University in Prague. It is claimed to be the oldest non-military technical university in Europe. You see that it is always important to find a subset where you are first in. I was thinking, putting here 1 year when the university was founded, and then I found out that it is quite complicated. So I put here the 3 most important years. So this is the university. It consists of 8 faculties, and this conference is organized in collaboration of 2 of them, the oldest and the youngest. So the youngest is the Faculty of Information Technology, where I'm from. The oldest is Faculty of Civil Engineering, where Hanna Najmanová is from, related to the fire engineering mainly and evacuation stuff from that side. So at the Faculty of Information Technology, there was the workshop yesterday. I think it went quite well, or at least I've been told so. And now we are at the premises of Faculty of Civil Engineering. Regarding to the participants, welcome to 12th edition of Pedestrian Evacuation Dynamics. Till yesterday we had 137 registered participants. Today we have 1 more. About 40% consisting of PhD and other students, which I found quite a lot, which is good. We got 130 submissions, 60 accepted for oral presentation, 60 for poster presentation, and you could see outside that we have only 41 posters, but still 101 contributions to be presented here. So I hope you'll enjoy all the all the presentation, all the science here present. I would like to thank the scientific committee for significant help reviewing and helping us to choose the proper contributions. So thank you very much. Your work, unfortunately, is not done yet. We will ask you to review the proceedings paper after the conference as well. So thank you for that in advance. We'll go to you by email. I would like to thank for all the support we have to both faculties, giving us institutional support, which enabled to do it with, I think, a reasonable fee. Our conference secretary, who is helping us with the technical stuff, the Academic and Medical Conference Agency, and I would like to very much thank Thunderhead Engineering for sponsoring us. Brian Klein is here representing Thunderhead, so you'll definitely meet him somewhere. You can find him in the crowd. Regarding the organizing team, here just want to see the faces, whom to look for. So to the left is the Faculty of Information Technologies, to the right the Faculty of Civil Engineering, and 2 people representing here the conference secretary with whom you should solve all the issues regarding technical problems and other stuff. If you struggle whom to ask, find the people with the blue stripe. He'll know what to do, or at least know where to send you, or know someone who knows, etc. Cool. So this is introduction of the premises. I will shortly go to short information, which would be the starting point of every day, just explaining you a few details. I just want to say that hopefully all presentation will be recorded and are streamed to YouTube channel. You all got the link via email, so it is not necessary to write it down at this moment. We will record and stream the slides and the sound just as a backup and opportunity to watch the parallel session you missed, for example, and we will let this available for a month after the conference, so we can go back to the presentations. If you don't wish your presentations to be recorded, just say that you don't wish this to be streamed and recorded, and it's not a problem to us. Just make sure that the technician knows to switch the screens properly. And final information is today's social event. Today's social event is a concert in Bethlehem Chapel starting at 7. So I please you to arrive in time. And because we are in Prague, we decided not to organize any buses because that would be a complete mess and you would stay for an hour there. Prague public transport is very good, so we recommend you to use it. The official program ends at 16:30, so you'll have 2.5 hours to refresh and get there. You may combine this with sightseeing. We have recommended several routes, the short ones, the nice ones, as an inspiration. You can find all of this in the participants' information where this QR code is directed to. Okay, the simplest way is just going to the metro, going to Můstek station and then walking. It is about 10-minute walks. If you'll really be insecure about getting there, just a hint, some organizers will leave at 18:15 from in front of the premises here. But yeah, I think but you'll miss some sightseeing before that. Okay, so this is regarding the introduction. So welcome to pedestrian evacuation dynamics and enjoy. I missed to put the enjoy slide there, so enjoy. And now I will give the words to the keynote, or to the chair of the keynote session, which is me, introducing the first keynote speaker, who is Mike Boltz, the head of division of pedestrian evacuation dynamic-empiricism, right? Whom I consider to be the leading person in data acquisition from pedestrian experiments and this empirical kind of part. His keynote is linked to yesterday's workshop, which was really a practical seminar focusing on this data acquisition. Thank you, Mike, very much for helping. Thank you, Alica, for helping as well. It was a nice occasion. Just a personal comment. I think I met Mike first in 2013 at TGF in Jülich, and I'm not sure whether it was there or at the next PED, but I found snapshots from Marek Bukáček's and mine research in his presentation with a reference the other guys from Czech doing experiments. So I want to introduce you the other guy from German doing experiments for the first keynote.
Okay, thank you very much for the kind introduction, Pavel, from the guy also doing experiments here in Czech Republic. So, hello to all of you. Impressive number of people here around. I think it's a much better time to give a presentation than last TGF, where I had the very, very last slot. So there were not that much people around anymore. So yes, thank you very much to be here. I want to give a presentation about empirical research in the field of our research field, in the field of pedestrian dynamics. I want to start with an overview about empirical methods, then focus on controlled experiments because we are most expertise have we in this area. Then again focus on motion capturing data because this is the most important data type for calculating the dynamic inside a crowd. Give a short historical review, then show the methods we use to extract motion data from our experiments, then show how we fuse the data. And the last thing I want to talk about is open science, especially open access data, because it fits to this talk. And I think it's a very important topic, especially because we are a very small group of people doing this type of research, and we need open data to work and have a growing group of people working in our field. Okay, this slide, maybe some of you have already seen this slide, 2008, 17 years ago at my very first PED. It was not 2013, as you said, where you met us the first time. I've been there 2008 already, in Wuppertal it was. And I've shown this slide exactly, oh, not exactly. The simulations were not already there. They came up 2 years later. And the hint that Mohsin gives a talk about model validation today is what also not on the slide, but other statements are still correct. The goal of our research is that we want to increase the safety and comfort for the people, and we want to increase the performance of the pedestrian facilities. And this, I think, we mainly want to do with computer simulations, and therefore we need reliable empirical data to get an idea what's going on in a crowd, to see influencing factors, to get an idea how we can set up models. And when we have designed our models, then we should calibrate and validate them. You see our first steps in this video that we want to have the same velocity density relation in our experiments, here with a single file experiment, and we want to have also the same flow inside through a bottleneck. I want to start now with the empirical methods, the options we have. And I think there are 5. The first one are field studies. Field studies are the passive field observation and data collection in natural settings without equipping the people and without telling them what to do. On the right-hand side, you see some pictures with corresponding papers from people who are famous in this field. For example, for field studies, it's Alessandro Corbetta. He's somewhere around. Yes, here. Yes, he's doing detection and tracking with help of 3D devices in field observation. The second option are controlled experiments. There we can distinguish between 2 different types. The real environment for controlled experiments, for example, evacuation drill, and you stop the time that people need to evacuate the building. And another option in controlled experiments is if you build up your facilities on your own, and as we do it mainly, as you see it on the right-hand side from Jun Chang. That's the second option, the controlled experiment. The third general method you can use are virtual, augmented, or mixed reality studies. The difference between them is that the virtual reality study, the whole world is virtual, what you show the participants. For augmented reality, only you have overlaid pieces of a virtual world on a real scenery. And for mixed reality, you also are able to interact with the virtual object, for example, virtual agents. And here I took a picture from your wife. Yes, I think she's made very good work and already has done this very early in our research. And the fourth option are the interviews. They are very important to know what's going on in the mind of the people. We can track people, calculate velocities, densities, but we don't know why this happens. Not in total. So we need to ask the people, why do they queue? Why do they overtake? Why do they do what they do? And only interviews are the possible option to do this, and is often combined with other methods like virtual reality studies, and then ask them later on why they have chosen this way or the other way. Okay, and the last option we have are the comparison with other systems, for example, with traffic, with granular flow, or with other modes of transport. This is also a reason why we have a TGF together, because we have similar methods included. That's we compared with other systems, also with systems with other self-driven particles like animals and, for example, sheeps. Yes, sheeps. And where's Claudio? Crabs and ants. Where's Andreas? There. But also robots. It's again you, I think. You have done this. Yes, we try to get ideas from other self-driven particles to learn a bit also about pedestrian dynamics. Okay, now I will go through the first three options and show or tell the advantages and disadvantages, and show one example what we have done with this in Jülich, starting with the field studies. The field studies, the natural behavior in real building infrastructure, including strong emotion, and this is the reason why we do not have to validate the transferability to real life, because it is real life. You do not have an expense recruitment of the participants. You do not have to pay them a fee. You do not have to build any construction. It's already there. You don't have to pay no one, just maybe buying some sensors. There's no expensive recruitment, as I said, and we have a large observation space. For example, in this picture, you see here, I will try this pointer the first time now. Wait. There's only one picture in the slide, so it's not that hard to find out, but I will also learn how to use this pointer. No. Ah, here it is. This picture. You see, it's a large observation space. We normally have not in controlled experiment, because to pay that much people, the participant fee would be too much for our, yes, what we have. And it's also the reason why we have often the possibility to have a long observation period. For example, when you're doing field studies at a railway station, day for day, you have very strong statistics at the end. You may also see some rare events, and you enable data-intense AI methods. And sometimes you're also able to use already existing devices, sensors like observation cameras or cell phones. The people, we are with them and use their Bluetooth and other signals to count people or to detect people. Okay, but there are also disadvantages. The main one is that you do not know what is going on in their mind. You don't know what they want to do. In controlled experiments, you can tell them what they should do. Here, you do not know what they do, and you cannot do a study to selectively change parameters, to study these parameters, but Alessandro will show us that it is possible also in field studies. He told me yesterday, I am very interested in this, who allows him to change the environment of a real setting. Okay, and then it's restricted to some observables. We can see only in a passive observation, and there's no reproducibility. So we cannot do it over and over again. We cannot do it somewhere else. If someone reads our paper, he cannot do it to compare his data to ours directly. So this is a problem, and the privacy issue is more complex. One example, what we have done in Jülich, Mira Küpper had a look at the waiting places for special waiting time on a platform at a railway station. We got trajectories. Yes, you make a photo, that's good, because we got it from you. It's trajectories on a platform, and she had a look where are the waiting places for special waiting time. For example, when the people are waiting there for less than 2 minutes, they are more waiting in this area. Here you see the seat map. When the people are waiting more than 10 minutes, they are more waiting here, where there's more space, and maybe they can sit somewhere. This is just one example for field studies we have done, but mainly our work is we are doing laboratory experiments, and the reason is because we are able to selectively analyze parameters of interest which influences the dynamic without any undesired influences, and we are able to vary these parameters. For example, in the top right video, you see different width of the corridor, and directly can measure the influence of the corridor width to the flow of the corridor. We have done this with 90, 100, 110 centimeters, I think is this example, but we have also done it with 120, 200, 220, 240, 300 centimeters. So we scan the parameters to see the influence of the corridor width. And you can generate desired situations, for example, very high densities. You not see that often in field studies. And set them exactly to a specific density, like in the bottom right video, where we set to 6 person per square meter exactly, and want to see how fast a person can move through this dense crowd. And it's possible to extract the quantities you are interested in. If you're interested in a heart rate variability, then you can put sensors to the body, or you want to have very accurate data of the motion of the head, you can put caps on the top of the head, so it eases the extraction of the data, and the data is typically of higher quality then. The privacy issue is manageable by declaration of consent, handing out them, and let's sign it like we have done it yesterday for our experiments. But there are also disadvantages. I will tell the truth here. The collection of the data is very expensive. You have to pay participant a fee. You have to rent a room. You have to build the construction and also pay for this. The situation is artificial, so the transferability to real life has to be justified somehow. Especially when you think about a dangerous situation, you ask them to move in a very high dense crowd with a high motivation. The people may think, okay, the researcher have a look at us, nothing will happen, and when this would happen in real life, they may be a little bit more careful. This is something what you have to justify. And some parameters influencing the dynamics are difficult to set up in an artificial environment. And the data, macroscopic data, is limited to in space and time because of the cost. And that's also the reason why we mainly focus on the tactical and operational level and less on the strategic level. One example again, here we made a study where people should leave an area through a bottleneck. You see on the top, here it is, on the top row, with a higher motivation, and the lower row with a lower motivation, and from left to right also with a corridor width in front of the bottleneck, which increases. And you see already nicely in the qualitative view on the videos, but also on quantitatively color-coded Voronoi cell with the density, that the density increases when the corridor width in front of the bottleneck increases and when the motivation increases. The third option are virtual, augmented, or mixed reality studies. They are the most flexible one. You can set up whatever you want, also dangerous situations with smoke, and you can define, fixate all parameters. You can, with this, show every person the exactly same situation over and over again, and you can show them the participant whenever you want or whenever they have time to do and wherever they are on the world. So it's independent in terms of time and place. You get directly synchronized data. It's also very helpful because the virtual reality systems need to know where the head of a person is and needs to know where the person, the head is oriented to. So you get directly already synchronized data because the virtual reality system needs to know where you're looking at to render the correct visualization of the scenario. And there exist very powerful game engines for something like this. Unity or Unreal engines are two of them. They facilitate the development of scenarios, and they also integrate a lot of different hardware. So you need something, a cave or virtual reality headset and you can port this easily when you are using such powerful game engines. But there are also disadvantages for virtual augmented mixed reality studies. It's the immersion. It depends strongly upon the quality of the visual and acoustic representation of the environment, and also the quality of the motion cycle of the person, the physical and social interaction, if the virtual person is looking at you and interact with you somehow. And also it's often less natural, the interaction. For example, in a virtual reality study, when you move in such an environment, it doesn't feel like it feels when you would walk normally in a real space, and often the force feedback is neglected totally, or if you have some force feedback, I know that Zina, I don't know if she already is around here. She uses something like a vibration bell or something like this to give some feedback, but it's not like you would really have touching a person in real environment. So it's least realistic, and so thus you need a validation for this. And some people have simulator sickness. Okay, an example where we use this. We ask a student at the University of Aachen to build us an environment to jump into the perspective of our own data, of the perspective of one participant in our experiment. Here you see the experiment. And we gave him this data, and he produced a visualization for this on the right-hand side, because we want to have an experience of the visual restriction for different spots, for different participants, and also may feel the proximity. We know that we can go further on to have maybe also the motion cycle included. The best would be, I think, to have something like on the top right. Okay. That's all about different types of empirical studies. Now I want to concentrate on controlled experiment, as I've already said, because that's where we have the most expertise in. Yes, we have done already a lot of experiments in the last 20 years when we started this research in Jülich and studied a lot of different influencing factors. You can divide these factors in individual factors, in group, or factors which come from the people with whom you are there or directly around you, or with factors coming from the whole crowd, or with factors coming from the environment, for example, the infrastructure. Some examples I framed in green. I framed an example where we made an experiment with wheelchair users, so disabled people or blind people. I see Paul here around. He made this study together with us. Then we have already shown the experiment where we changed the motivation. We also had an experiment where we asked older pupils to stay together with or keep care on younger pupils in a school and go together through a bottleneck. Here Andreas has done this experiment with us together at two schools. Then the factors from the crowd could be the direction, bi-directional or multi-directional streams, as you see in this yellow framed experiment. And the infrastructure we changed a lot. We had experiments in crossings, T-junctions, corridors, corners, stairs, and changed the width, the height, the length of these facilities. And you can group the data coming out of these experiments in three types. There are the global static information, which stays the same for the whole experiment and is the same for every person. For example, the facility design. And another thing could be what you say to the people. If it's the same instruction you give to everyone, the same motivation to give to everyone, this would be also a global static information. Second group are personal static information, which is the same for the whole experiment, and but is different from person to person. This type of data you can collect when you give an ID to the person. You can connect this with directories. We see later on by code the people with a cap and hand out questionnaires, and then you know the age and the gender from a person moving around. And the most complex data is personal dynamic information data. The physical one is where do the person moves, especially we often extract the head directories, or also where the body parts are in the crowd. And then the perception is what do the people see, feel, and hear, and the physiological information could be arousal or behavior. These are the sensors we use to get this data out of our experiments. For the position, we used cameras, multiple cameras, overlapping cameras to cover a larger experimental area. We use motion capturing system to capture motion of body parts. For the sensory perception, we started to use eye tracker. We have used pressure sensors and we use microphones. And for physiological response, we have used heart rate variability sensors and electrodermal activity sensors. There exists a lot of other sensors. Maybe you use other sensors. I don't want to go through them, but I want to point to publication, very good publication, 2 of them from people who are around here. I've seen also Vinny somewhere. Yeah, there are 2 very nice books, one from Claudio Feliciani. It's Introduction to Crowd Management, and there's a chapter 4 called Pedestrian and Crowd Sensing Principles and Technologies, and from Vinny, it's the book Walking and Pedestrian with a chapter 4 Data and Data Collection for Pedestrian Planning, and there you can read a lot of all other choices you have to extract data to learn more about the dynamics. Okay. Now focus again to motion capturing, because this is the main data you need for calculating the main quantities like velocity, density, and flow. I will start with a historical review, and I like to start 1878 with Edward Muybridge. He has been asked by Mr. Stanford, the founder of the Stanford University, to tell him the motion cycle of his horse. He was interested where are the feet of the horse to which time, and yes, he was a horse enthusiast, and you see the results on the bottom left what Edward Muybridge did with his new techniques chronophotography. You see this built-up structure on the top right. It's a series of cameras which take a series of pictures triggered by tripwires here on the ground, and then getting a series of pictures, putting them together, you get a motion cycle of this horse. When he had built this, he also did study the motion cycle of other animals, but also then he had the idea also to analyze or to at least visualize the motion cycle of humans. And here he is himself walking up some steps. It's Edward Muybridge himself. Okay, but we mainly interested in the dynamic in crowds, not of individual motion. And I think the first people where we got quantities we can use came from Henkin and Wright in 1958. They just used stopwatches and counting people. So it's on the macroscopic level where we get a velocity density relation. So we have already something like a fundamental diagram of people walking to that time. And it stays the same data type, the same granularity. When Fruin did his experiments or observations, he made it much more careful or much more deeper. He was also interested in the space requirement of individual people, the spatial Wahrnehmung. Help me. Thank you. Yes. He had a much deeper look to different systems, but at the end we only have this quantities like velocity and density for the whole group for some points in time. And then we had a very important step Serge Hugedorn did, where also Vinny Dahm worked with in 2003, experiments where they recorded the experiment from a top view and extracted the position of the head with the help of colored caps and used a computer vision technique. And we got trajectories from each person to every time we got the place where they are. And this was a very important step. This was this time when we have microscopic data for our research, although we know that the models already started in the 1990s to be microscopic, the social force model, but we had no microscopic data to validate exactly where the people move. Okay, the next step we made using stereo cameras to have a bit more accurate 3D trajectory, also including this bobbing while you are moving, this up and down. We can capture with help of stereo cameras, but also when we are doing experiments on stairs, as you see it here. This is we do with help of 3D devices like stereo cameras. I will come to this later on to explain what's going on there, or how we did it. The next step, I think, is also important. We use it nowadays also. It's about identification of people. Who is this? Who we track in our video recordings to put codes on the head. Daniel Stewart published this the first time in 2013. He did it to know who are disabled people in the system, because he did experiments with wheelchair users, and also to stitch the trajectories of different cameras together. So he has one trajectory for one person each. Okay, up to that time, only every person is only a point in space, but we know that we are not only a point in space, hopefully. We have some assumptions of the size of the body, but no more. And then in 2013, the people started to extract the orientation of the upper body, because this is the easiest part to detect also with cameras, and also which is very important for the space requirement, the space usage, the shoulder orientation, shoulder position, starting with step sensors from British and the optical and using an optical motion capturing system or markers by Mineko Imanishi. I've also seen her already there. And the inertial measurement unit was used by you, Claudio, again, and showed us, and I think it was China Hefei in 2016 at this PED. Okay. And the last step, what I would say, we tried our best to introduce it to our field, is using full body motion capturing system to really have a full body motion inside a crowd. Full body motion is no problem with optical sensors, but to have the full body motion inside a crowd where you do not see the legs and arms, we introduced how you can do it in 2019 at the TGF by use of inertial measurement unit based motion capturing system. Yes, I will go tell something about this later on. Okay, this was a historical review, and I want to show methods we use to extract data out of our experiments. And we mainly use cameras for our purpose, and I think most of you use cameras because they see the world like we as humans see the world, and this vision enables the most natural manual study. When you look to the video here, you see how the people merge, how they behave, where are the arms. Also already stepping without seeing the feet, you see this little swaying from the step the people are doing. Sometimes you also see arms where they give away. And also when your camera's looking to the face, when they would not have wear a mask at that time. You could see maybe how they feel, how happy they are, how the mood is in the crowd. But there are also disadvantages, the advantages goes on. There's a high resolution to extract a lot of features, and they are cheap because there are a lot of cameras around. They are adaptable to your needs. You can have high resolution to capture, for example, here extract the code out of the video recordings, or you need a high frame rate if you want to capture fast motion, or you want to have wide angle lenses to see the whole experimental area in one image. And there exist a huge number of existing methods, especially inspired by our own perception. But there are also disadvantages. We have a high resolution, a high frame rate, so we have also a lot data we have to store, to handle, and to transport. And the complexity of methods limited for real-time application. If you have, for example, field studies and you do it 24/7 a year long, the amount of space is very large, or you're not allowed to record data, then you need methods in computer vision which enables you to do real-time extraction of data. Okay. Here, these steps, yesterday we had a workshop where we talked only about this one slide, how to extract data out of video recordings. We normally start with an overhead video recording to have least occlusion. And you see here a bottleneck setup again. We have to do first an intrinsic calibration and get rid of the distortion of the lenses. And therefore, we are doing an intrinsic calibration here with this chessboard coming from a library OpenCV. And then we get rid of the lens distortion. And we have intrinsic parameters like the focal length and the center of the optics where the optical axis go through. With this, then every pixel covers the same volumetric space. The next step, what we have seen here, going with the pole through the scene to know for some points in the image where it is located in real 3D. At the end, with this extrinsic calibration, we have then a 3D world coordinate system and this should be the same for every local sensor which is measuring in space. And you see it here, there's a blue, the result with the blue coordinate system and the quality with this 1x1 meter grid on the floor. Okay, now we have done the calibration, fine. Next step is that we want to detect the people going below the camera. Here are the people wear green caps. You can detect them with the green caps, or if you have a camera with a high resolution, you can also read out the codes. The code help us to know who wears which sensor, which is the age and the gender of the person, and also to know what is the size of the person, because this is important. Up to that time, we only know, we have calibrated it, so we know from the optical center to every pixel of the image where this line goes through the real world. But we don't know at which distance the head of each person is, and that's why we need the height of the person to have the correct position on the floor. You see this green crosses. This is the position on the moving plane, and this is what we need to have in 2D, the velocity, density, and flow. That's why we need also, for example, these questionnaires. Okay, now we detect the people, and the next thing is then track them from frame to frame to have a, one trajectory for each person, and also have maybe a position at a place where we could not detect the person with the help of the codes. And we can then connect with the codes also other sensors. As I said, here you see the connection with our motion capturing system, where we can nicely see where also body parts are we cannot see with the camera, with the feet, with the arms, where they are, and how they rotated, how they merge through the bottleneck. Okay. With this type of technique, with cameras, camera recordings, we are now able to extract trajectories. We can also extract the head orientation when we are using special markers which have a line on the top, or these codes also have an orientation. We can also extract the points maybe on the shoulders if we have not too large angle of view to get the knowledge of the shoulder orientation. But when we want to have the 3D information, for example, when people moving on stairs, we need 3D devices, and we use stereo cameras for this. And you see on the left-hand side an overview, a video of our experiment where we mount on the dolly here a stereo camera with a perpendicular view to the people here. In the center image you see, or video, you see one of the images of the stereo camera. And the stereo camera has two images, and the disparity, so the distance of the same point in real space on the image plane sensor is the disparity, and it directly corresponds to the distance to the camera. Here color coded the distance, and at the end you get then the trajectories in real space in 3D, color coded due to the color of the corresponding to the color of the shirt of the people within the experiment. Okay, now we have our trajectories. But we have to be careful when we want to get quantities out of these trajectories. When you want, for example, to calculate the velocity and you would not smooth them to get rid of this swaying coming from the bipedal movement. You see it nicely in this video that is also dependent on the velocity of the people. When you would not smooth it, you will overestimate the velocity. So you have to do a smoothing there if you want to have the main movement correction, maybe to see the relation of the body rotation, the upper body rotation in relation to the main movement direction. You also have to smooth it, or you want to know the lane formation as you see it in the right figure. You also should smooth it to see how the lane formation dissolves when the bottle or the corridor width increases. Okay. When we are more interested also what's going on in the crowd, the interaction of the body, how the people merge into a bottleneck, how the physical interaction is, how they use the space, how the body posture is overtaking and passing each other. To understand what happened there, you need to capture also body parts. Best would be the full body, and then we are enabling also to have 3D models. I like to point to a talk of Thomas Chatagnon this afternoon. He will talk about 3D models. And how do we do this? As I've already said, you are able also to track the shoulders with camera data, but we also try different other sensors like inertial measurement units. Jette used in our institute. We also use 3D cameras and machine learning technique on images or also on 3D point clouds. Dennis Kielich is using this, and he will give a talk directly after this slot. He will compare different possibilities how to extract shoulder orientation out of experiments. And when we want to have the full body motion, especially when we want to know where are the feet, where are the arms, where are the hips, we are using a 3D full body motion capturing system based on inertial measurement units. Inertial measurement units are system which, like your smartphones, measures the acceleration, the angular rate, and the magnetic field. And with this full body motion capturing system, we have a biomechanical model, and we have 17 of these sensors placed all over the body for differentiable segments. And with this sensor information, the company Xsense, where we used our what we used, build up then a biomechanical model, the full body motion of a person. We use it because we cannot use an optical system because we cannot see the feet and arms in a dense crowd. So we need something which is self-contained and light-wise, and these inertial measurement units are like this. And then we are able, you have seen already these stick model or as an overlay on the videos. That's the result what we get out of this. But it's only a relative motion. The motion capturing system records the motion of the body cycle, but we do not know where this motion happens. So we have to combine it with the absolute world coordinate system coming from the cameras. And in general, when we want to fuse data, combine data, we need a calibration and synchronization of the data. First, a spatial calibration, especially when we want to combine multiple trajectories from multiple cameras. Then we need a global world coordinate system for each camera. Then we need also a time synchronization. Oh, yes, this was yesterday, Pavel, you. Yes, with the balloon you can also do setting a time, use different methods to do this. You need it for every sensor. You want to know which data objects the one sensor belongs to which data object in the other sensor. It's very important for every type of sensor, not only for cameras or motion capturing system. And you need a person mapping. When different sensors are worn by different people, you need to know who was what to which time, and it's the third point, the person mapping. Okay. Did everyone count the time correctly yesterday? From bumping the balloon to when they pass the bottleneck? Not everyone, so you have homework for the people who haven't done it up to now. Okay, when you want to fuse data from the positional data coming from the camera and the Xsense system we use for the full body motion capturing system, as I told you, we have only this motion in relative motion of the people, but we want to know where this relative motion happens in in the experiment in the crowd. Therefore, we have to combine it, and it's very easy. We smooth both data set and look for the same data point in both data sets. Smooth the trajectory, the head trajectory coming from the camera, and also the head trajectory coming from the full body motion capturing system, and then calculate the translation vector and calculate the rotation. We have to do it every second, because the inertial measurement system has a drift, so we do it over and over again, and at the end we have then can put the motion data, the full body motion data, into the crowd with help of the camera data. Okay, here now I want to show you 3 examples where we use it or where we need this. Sina, you see your work here, and Jule. It's about pushing people from behind with a what's called the punching bag, and you see on the left-hand side how they propagate this push to this one line by the full body or by the hands. And you see in this video people are standing 1 elbow distance in front of each other, so there's a little distance between the people. And we have done this also with a distance with no distance, when the people are directly stand behind each other. And you see in the figures on the bottom right, in the x-axis is the time, and the y-axis is the moving direction from left to right. Is this y-axis from bottom to top here, and you see here the point when the person starts moving. You first see that also the last person moves when you have no distance between the people, and you see that this curve is steeper than the one on the right hand side, where the people have a distance of an elbow, like you have it in this video here. And you see that it's the velocity is lower, how the push propagates, and it's not that far how the push propagates. So you learn here that for higher densities, the speed and also how fast a push propagates and how far a push propagates increases. Okay, second example where we use this inertial measurement based motion capturing system together with our camera system is where we have a look how people move through a bottleneck. In the first upper row, we have people moving through a bottleneck on their own individually. We have done this really because we had Corona, and we were not able to do crowd experiments, and then came up with the idea, study first people moving individually through a bottleneck. And this is a result. You see on the top individual people moving through the bottleneck, and here we see 4 people encountering at the bottleneck. And it's both in a hurried condition or higher motivated condition, on the top with 40 centimeters bottleneck, and on the bottom 80 centimeters bottleneck. And we have done this for different widths, especially for the individual people. And you see in the diagram here and here, on the x-axis is the distance to crossing. So from here it's 0, and starting 4 meters distance here is here on the x-axis, and on the y-axis you have the absolute rotation of the upper body related to the main movement direction. And you see here the different color means that it's the different bottleneck widths, and the dashed line are low motivation and the solid line are higher motivation, and the smaller diagrams show where the same values for the starting angle, 90 degree, 60, 30 and 0 degree. 0 degree is the largest one. You see that the rotation increases for smaller bottleneck widths, for higher motivation and for larger starting angle. For all these 3, the rotation increases of the upper body. On the 5 minutes left, okay. Really? I tried it before. 4 people encounter here to this bottleneck, and you see in the figures the same, that the motivation increases the rotation, then also the motivation increases the rotation, but also you see that people who are the first or second or third have a higher rotation than an individual person, because the people have time only, the possibilities only to change their way to make a longer way to the bottleneck, to increase or decrease the speed, or to use their body to optimize the space usage. That's the last option when they pass the bottleneck. Okay, this is the third third example where we use this full body motion data inside a crowd about steps inside crowd, but I heard I have not that much time. That I just point to Karina, who will give a talk on this on Friday morning. I will not talk about it now, because I want to tell something also about open science, about open access data, which fits to this talk. And I think open science is very important in the full research cycle. From the open source code, it helps to not everyone has to do it on their own. We have, for example, for the simulation of the modeling part, PED25. For extracting trajectories, we have the open source software PTrack, and for analyzing these trajectories, we have the software PED25. We are supporting also the open access, the Diamond Open Access journal, Collective Dynamics, and we signed already in 2023 the DOA declaration, an alternative reputation system for us researcher, not only looking at the index of companies and more taking into account the software you write, the data you share, what you're doing for our community, doing reviews. All this stuff should be also included in evaluating the quality of you as a researcher. And the last thing is open data. And I think open data is important, as I want to tell now why. Open data, only with open data, there's a reproducibility of our findings. When we write a paper and we give not the data with it, and the others cannot reproduce our findings there. The best would be also to include the software directly so they can see what we made. Maybe also when there are mistakes, they can look for this, and also when they can reuse it. Because it's very expensive to make laboratory experiments. It's not good that we all have to do the same experiment again, but we can, and then we directly can compare the experimental data from us and the others. The visibility increases not only to the data, also to the researcher who has done the experiment and is responsible for the data. It eases the collaboration between each other. And now the most important thing, I think, it's a faster dissemination and thus development in our research field. So when a student at the university has not to do an experiment again, or he's not able to do an experiment because he has no money, but he can work on this topic just by taking the data from us. So I think we can increase the number of people working in our field when we share the data, and I think the field speed up, we get more findings at the same time. And it's equal access also for developing countries. It increases the reliability. And data citation also improves the own evaluation measure, especially when we think of also putting it to our, when we have other declaration of consent, other research assessment like DORA. When you additionally standardize our metadata and standardize the data formats, it's easier to compare the research and to reuse the data, and it enables also data-intense AI methods. But there are also disadvantages, I will tell the truth. You have to do a little bit more. It would be also good to do this also for people after you at the same institute, but especially when you publish it, you will write down what's in the data, name it correctly, and explain a little bit about the data. This is a little bit more work. Then you have to consider the privacy of the individuals, for example, discuss faces. And I think the most important why people don't like to do it is someone else might discover something in the data that you might have discovered later. This is true, but I think not only the number of points is more on the advantage side, also they are stronger, the reliability and so on. I think it's more important than these points. Okay. We have a data archive for all of us. We have 60 visits a day. I don't know who is visiting our website. It's not Roberts, it's not us. I don't know who's visiting, but you see the people use it. And And we also host data from all of us. If you are interested that we upload it there, you can also upload it to Zenodo. Then maybe you send us the link of your data, then we can include it in the long list of link list of data sets. And I want to encourage you to share your data to us, to somewhere else, and just tell us where the data is. Okay, then we want to 2 minutes. Yeah. I see the. Okay. Yes, we want to do our data more fair. What does it mean? It should be findable, accessible, interoperable, reusable, and therefore we set up a metadata schema. And for all our experiments, more than 60 and more than 2,700 runs we have, 2,700 runs we filled this metadata of the where it is, who was responsible, how many people, which parameter did we change, who was the founder for the experiment, and for everyone the different parameters and a link to the data, a link to the description, a link to the videos, and all included in one metadata. And we mirror also this metadata data site and other repositories like Wikidata to make it more findable. And we standardize the data formats. For example, for the directory data, we have based on HDF5 file format, standardized type where we also include all the metadata directly to the directories, also the geometry we use for these directories. We also use the same data set for 3D motion, C3D, so it's not from the vendor, it's something what all people can use directly with open source software. And we have also now the same setup structure, so it's directly we can use it for calculating and make our visualization. We have also a dashboard for searching, access the metadata. So, but you see the checks, but 2 of them are only yellow. Green is fine, we are finished with it, but findability could be better because the dashboard, the yellow frame things are only accessible by us. So the raw data is only accessible by us. The database is only accessible, but all what's in the database, we stream it as a JSON file to our data archive, so no problem. But I see a problem, the dashboard is only accessible by us to easier search within the metadata, but it's only a technical problem. I hope we solve it within the next years so that also you are able to search and access direct the data from a dashboard, because it's much easier for all of us. And I have only a yellow check at the reusable, because up to now we only share the directory at the end in metric space, and we only share overview videos to get an idea what's going on. But it would be interesting to have, especially when I talk to people who are doing machine learning, to have really the raw video material and the pixel coordinates of the directory to make something else with the data, to find automatically pushing behavior or something like this, where we started with. This could be an enhancement of the data archive to add this, and then we have also there a green check mark. Outlook, you want to improve the PED models. I think every one of us want to do this. I think full body motion is important. I think perception is important. I think psychological aspects are important. Therefore, we need more reliable empirical data. And for this, it would be very nice to have an open open pedestrian laboratory. As you see it here, I only know this Pearl platform at the UCL at London. And to have something for our community where we can do experiments and directly stream out the extracted data and don't set up again and again. It would be very nice. It could streamline and speed up the performance of experiments. Just a wish. And last thing, enhance and expand our community open access data archive. And now the last slide, excuse me for being late. The people you see here were involved into the slides I have shown to you. It's not only my work. And the people are framed in red are also do something for this conference today. They have a talk or are co-author of one of the papers or abstracts here. I think there are a lot of people working on this topic further on. It's nice. And yeah, that's my last slide. I thank you very much for your attention, and I'm happy to ask your questions.
Thank you, Mike, very much for the lecture. Sorry for speeding you up at the end, but I think this definitely deserves a discussion, and we have about 5 minutes for discussion. I've seen several hands.
Thank you, Mike. What a ride through the history of observation of pedestrians. I have a challenge for you. We use your data a lot for validation. And nowadays I see, I'm a modeler, I'm Gerta, by the way, Munich University of Applied Sciences, and we use the data to validate our models. And I see a lot of new AI-driven models coming along, and they are so rich in behavior that locomotion is just like a side effect. And I'm wondering, what kind of experiment do we need to validate those?
Okay. I think we
I'm
should
really worried
ask
about
people who are building models, but I give it a try. I think for machine learning, often also field data is a good choice. Then you can model especially what's going on at this special place, because the machine learning models do not describe the influence of special parameters, but they can maybe very good describe for a special situation what happens there. So I think we need then a lot of data, more data, I think, for machine learning, especially when we also want to want to know also minor changes in the geometry to include in such data. Machine learning cannot explain something to you what has not seen before. So you need data, every data, what can be in the real environment. So I think we need much more data when we want to have reliable models on basis of machine learning techniques.
You said that it is important to make data from experiments publicly available. I agree, but I think it is even more important not only to publish the data, but to explain in detail how you did the experiments, because that's what you need in order to reproduce the results. And nowadays, because Gerta mentioned AI, I mean, I know cases from other discipline actually where there was public data which was fake. And that's many people actually work with fake data, and all these errors propagated. And that's something that we need some mechanisms actually to prevent that in our case. So is there sort of a feedback loop so that you can actually, if you downloaded data and you feel that that's maybe something is suspicious with the data,
Okay.
I think that we need some sort of mechanism to make certain tests.
Okay. I think there are two questions in your question. It's one, it's about fake data. Yes, I hope we don't have fake data, I can say, but we have errors in our data. It is, and I am happy that people use our data, and we often get a feedback when there's something going wrong. That, for example, directories go through the boundary of the wall, or there is drop off a directory. And I think it's useful that we get this feedback to improve the data. But it's also on the disadvantage side of the work of a researcher, because then you have to work on your data again. On the side, the first part of the question, I think it was that you should name as many aspects as you think of. You don't know what in the future may people think have an influence. For example, the lighting condition. Up to now, we do not measure the light at the place where the people go. We do not measure the reflectance of the wall, how the walls are produced. Just an example. You could think of also try to put all this to the description of the data. We also started now to make a larger publication from data sets, so describe more the distribution of age and gender, so you have more data, more idea what's really going on, how it was performed.
So probably there's some obvious data that should be included, and some data that is not so obvious and only turns out to be interesting later. Yeah.
Mm.
Okay, I think we have time for last question.
Mm. I think I will point to Alessandro because he had a lot of data. We have only the data of the experiments. They are limited in time and space, as I have said. You're right, when you need a lot of data, then field data is much more rich in time and space, and it's, how to say, easier to gather more data because the people are there anyhow, so you don't have to pay them. So that's the reason why you have more data. When you need them for your models, yeah, I point you to Alessandro. He can maybe share it with you. Okay.
I think that there will definitely be more questions, so we can postpone them to coffee break because Mike has one more announcement before the coffee break.
Yes, I like to ask people, the editors of our journal, Collective Dynamics, come to the floor because we want to announce something for a special issue for the 10th anniversary. And I like to hand over.
Thank you very much. Probably most of you know our journal Collective Dynamics, which is sort of a spin-off of this conference and the sister conference Traffic and Granular Flow. And so the journal will now have its 10th anniversary. And one of the reasons, besides being a spin-off of the conference series, why we founded this journal 10 years ago, or even more than 10 years ago, was that sometimes, you all know that, sometimes it's very difficult to find an appropriate journal for research. Because often the research is interdisciplinary, and then it's rejected by physics journals because there's not enough physics in it, or rejected by engineering journal because it's too much psychology in it, or whatever. So that was one idea, to have a journal which is very broad, and we intend not to reject any paper being out of the scope of the journal, right? So that is why we think that this is kind of a very important contribution to the community. And now we have the 10th anniversary, and we have one of the problem with the journal is that it's not listed in all of the relevant indices, like Science Citation Index. To get listed there, you need a certain amount of papers that are published and a certain amount of citations and so on. And so far, we unfortunately have not been able to reach that. And somehow to promote the journal a little bit and to celebrate the 10th anniversary, we want to start a special issue for the 10th anniversary. And we ask you to submit your work. And it can be anything. So that's also, I think, unique for this kind of journal. So it does not necessarily have to be a normal research paper. We also accept systematic reviews, or you can have your lecture notes published there. And that will all go through the usual refereeing process. And for the special occasion of the 10th anniversary, we also will give out a Best Paper Award, and we have up to €2,000, so which we can spend on the prize money. So we don't know how many papers will get an award, but total €2,000. I hope it's not too bad. So we encourage especially young researchers to submit to submit papers or lecture notes or reviews or whatever to the journal. If further information will be sent out using the mailing list of the journal, so we get more detailed information about deadlines and so on. If you're not on the mailing list, so please subscribe. So go to the journal webpage. Is it on here? No. That's not. But no, it's below the QR code. Below the QR code, and then you can join the mailing list. From the mailing list, you also get updates on the conferences. So for the TGF and the PED, you always get the newest information. So it's worthwhile to join the mailing list. For this special issue, we have already some contributions promised from Michael Schreckenberg, for instance. He will write sort of a preface. As you know, he is the person who started this conference series, PED, and also the TGF. we will get a paper from Dinesh Manohar, who was actually the first contributor to the journal, so he published the first paper, and Bernhard Mittermeier is person responsible for the technical and organizational issues of this Diamond Open Access Journal.
Yeah, he leads the library who published our journal, and he loves open science and also Diamond Open Access data. He fights for this also in committees, and that's why he also loves to say some words or write something in our preface.
So, yeah. First step, please join the mailing list, then you receive updated information, and think about a nice topic that you can submit for this special issue. Anything that I forgot? Okay, looking forward to your contributions.
Coffee break.